Hello, I'm Aubrey Machin, the National Technical Sales Manager for the Proctor Group. I'd like to welcome you to this webinar giving an introduction to VOC barrier membranes. With the increasing focus on resolving housing shortages in our cities, redevelopment of brownfield sites is becoming ever more widespread and bringing an increasing focus of site remediation and protecting building occupants from soil contamination. Today, we're going to look at some of the common issues affecting construction on contaminated sites, particularly those affected by VOC contamination, and discuss how barrier membranes can provide effective, safe and good value solutions. We'll first consider what VOCs are and where they come from before moving on to risk-based design and how it can be applied. We'll also be looking at the most common membrane types and pros and cons of each solution. We'll be finishing with a Q&A session, or should you have any queries throughout today's webinar, you can email them webinar@proctorgroup.com or type them into the comment box on this video stream. You'll be able to review this presentation and the Q&A afterwards, and you'll be emailed links once the event concludes. What are VOCs? VOCs, or volatile organic compounds, are defined in the Syria 716 document as organic compounds that are volatile under normal environmental atmospheric conditions. They may be found in the ground, in the solid, liquid and dissolved form, as well as in gaseous phase. VOCs can be both man-made or natural and have a wide range of applications and sources, being found in everything from paints and coatings to plastics and cleaning products. Hydrocarbon fuels such as petrol and diesel are also forms of VOC. While not all these compounds are harmful, man-made VOCs are regulated to limit exposure to those that are. In construction, the VOC content of products such as paint is restricted to ensure that the detrimental effects of indoor air quality and health of the building occupant are limited, and VOCs originating from contaminated land or other external sources are similarly regulated. VOC contamination can severely reduce the amenity of the building or structure, with particularly severe effects on sufferers of asthma or other respiratory issues. While some effects such as dizziness can be mild and short-term, contaminant vapours can also have carcinogenic effects or cause damage to liver and kidneys given long-term exposure. These effects can also be present during remediation works, and therefore exposure of site workers is also an important consideration. Let's look at the sources of VOC contamination. Naturally occurring VOCs are typically quite rare compared to other natural soil gases such as methane or carbon dioxide. So in most cases, building designers will be dealing with pollutants arising from historical uses of the sites. Most commonly, this will mean former industrial sites where chemical spillage may have occurred or where poor waste handling practice has led to a discharge into the environment. Such sites as former petrol stations or residential sites with fuel storage tanks can also require remediation to remove VOC contaminants. The most appropriate strategies for dealing with these contaminants will depend on the precise nature of the pollutants present on the site and the building's intended use. For example, petroleum hydrocarbons such as benzene, toluene or diesel fuel can, given certain soil conditions, attenuate more readily than types of halogenated hydrocarbons found in dry cleaning fluid and hence may present a lower risk. Likewise, a warehouse or storage facility will require a less rigorous approach to remediation than a dwelling or an office, all else being equal. These risk factors are both numerous and complex, and the Syria 716 guidance document outlines the processes involved in both assessment and mitigation. The first stage of this process is the development of a conceptual site model, or CSM. Based on information obtained from both historical desk studies and direct site measurements, the CSM identifies the potential hazards present on a site and their likely effects on subsequent human activity during construction and afterwards, as well as the implication for future development. Once complete, the CSM forms the basis for a succession of increasingly detailed risk assessments as the project progresses. This approach allows the remediation to be undertaken in the most efficient way possible. Some forms of remediation, such as the removal of the pollution entirely, can be difficult and expensive, and by ensuring that this is not undertaken unless required, a robust, safe and economical solution can be achieved through good design. The primary concept considered in these assessments is that of pollution linkages. These are chains of risk factors that, taken together, present a risk to health and/or safety. If, however, parts of the chain are removed, the resultant risk factors can be reduced or eliminated. The primary linkages present in every situation are the pollution source, the pathway, and the receptor. This source, pathway, receptor model forms the foundation of risk-based design strategies for ground gas and VOC contamination. Let's take the source. Source treatment involves taking action to break the linkage at source. The actual pollutant itself, in very simple terms, this involves achieving one or more of the following outcomes. Destruction or neutralisation, whereby the pollutant is rendered harmless through the use of some form of treatment, such as adding a degrading chemical agent or a process such as heat. Removal, which can entail either removal of the polluted soil and disposing it off-site, or extracting the pollutant from the soil. Immobilisation, or trapping the pollutant by adding chemicals to solidify the contaminants, making it impossible for liquids or vapours to escape. If we then take the pathway, a pathway management solution breaks the link between contamination at the source and the building occupants by two primary means. Firstly, barrier systems, which physically block the passage of harmful liquids or vapours either at the source or the receptor. Dilution or dispersal, where ventilation systems are used to reduce vapour concentrations below harmful levels. Ensuring barrier and ventilation systems work effectively over the lifetime of the building is critical. Both specification and installation of these systems is more complex than it may appear, with an array of physical properties, tests and installation details to consider. It is also not always possible to rely on the membrane to provide 100% barrier to the contaminants, so these systems are usually used as part of a wider ranging remediation strategy. The receptors, or receptor management, is the most problematic of the three strategies, mainly as it can come into direct conflict with the purpose of the building or structure by placing restrictions on the occupants which may prove unacceptable. For this reason, receptor management is most commonly used as a temporary measure while a longer-term strategy is developed. For example, restricting access buildings during decommissioning of an industrial site or evacuating residential properties in response to a nearby chemical spillage. Another more common example of receptor management would be the health and safety requirements placed on contractors during remediation works, such as PPE or safe working practices. Pathways in practice. Today we'll be considering pathway management in more detail, specifically the use of barrier membranes to restrict the flow of VOC vapours into buildings or structures. Barrier membranes strike a good balance between effectiveness, practicability and sustainability, making them by far the most common solution used in new build projects on brownfield sites in the UK today. As we briefly discussed already, these systems are commonly used in conjunction with other remediation measures such as ventilation or dispersal systems. A well-designed barrier system can reduce exposure to contractors during remediation works and reduce disposal costs associated with contaminated soils, helping to achieve the right balance of practicality and long-term durability. Membrane specification. When specifying geomembranes for VOC applications, it's important to remember that chemical resistance and vapour permeability are not the same thing, and membranes that are highly resistant to liquid VOCs may not be suitable in a VOC vapour barrier application. Conversely, membranes which resist VOC vapours effectively may lack the resistance to be used in the presence of liquid hydrocarbons. That's not to say the chemical resistance is not important, as the barrier must be able to resist exposure to adverse conditions in the longer term without negative effects to its performance or mechanical properties. It can't always be guaranteed that the VOCs will remain a vapour, as the water table may rise and bring the membrane into contact with the VOCs in a liquid form. It's therefore important to identify the most appropriate combination of physical properties for the application. However, this in turn is dependent on good test data for a range of chemicals being available for the membrane that's specified. The permeability of the membrane is governed by the following factors. Firstly, the concentration gradient between the clean and dirty sides of the barrier, the solubility of the contaminant in the membrane's polymer, referred to as partitioning. These two factors govern whether or not a vapour transfer will occur. For example, water is not soluble in HDPE, so will not permit transfer as the membrane surface will not allow its absorption. In contrast, however, benzene will pass through readily. The rate of transfer and how quickly equilibrium is reached is affected by the following factors: the molecular structure and thickness of the membrane, and the molecular size or shape. The material composition of the membrane dictates how much free space there is at a molecular level for vapour to pass through and how easy the pathway this provides. For example, a crystalline regular structure will permit the passage of gas more readily. Likewise, the configuration of the VOC vapour molecule will dictate how easily they can pass, some molecules being significantly more streamlined than others. As we can see, having these complex relationships easily summarised is an important factor in ensuring the design is appropriately tailored to the application. Membrane manufacturers must therefore ensure this information is available and presented in standardised form to allow specifications to be easily compared and the implications for risk assessment to be fully considered. Series 748 lists the following substances as likely to require permeation testing: benzene, toluene, ethylbenzene, MP and O xylenes, hexane, vinyl chloride, tetrachloroethane, trichloroethane and naphthalene. Designers should satisfy themselves that the remediation measures specified are appropriate to the conditions likely to be encountered on individual sites. Next, we look at durability. The actual VOC resistance is only one facet of membrane performance that must be considered. Membranes must also be able to resist degradation processes such as oxidation, particularly if they are based around foils. As part of an appropriate overall design, a membrane of low resistance to a liquid contaminant may still be suitable provided exposure to that liquid form is minimised. For example, by means of a source remediation or by ensuring that the barrier is located in the structure such that contact is impossible. In our example here, if the membrane is located underneath the structural slab, there is a risk the groundwater may bring contaminants from the source into contact with the membrane, which is a particular risk where the presence of water may act as a catalyst and increase the rate of degradation. To resolve this issue, the membrane spec could be increased to improve the chemical resistance, but this may increase the cost and make installation more problematic. It could also be remediated by removing the source altogether, but again, this solution may not be practical or economically viable. A more straightforward solution would be to simply relocate the membrane over the structural slab, which would remove the risk of waterborne contamination in all but the most extreme flood conditions. Under most circumstances, this would be deemed an acceptable risk. So we can see how taking a holistic view of design criteria can lead to significant benefits. However, even the best design solution is only as good as its implementation. Particularly when considering low permeability membranes, the physical integrity and continuity of the barrier is paramount, and the membrane must be capable of resisting the physical stresses of the installation process and the in-use circumstances. Installation and verification is therefore of equal importance to specification. While there are some obvious common sense considerations here, such as ensuring there are no gaps or punctures in the material and all pipes and structural elements are properly sealed, there are also some less apparent aspects to bear in mind. As we've discussed already, the thickness of the membrane is an important factor regarding vapour permeability, and this also means that any factors that may affect the thickness are important. What is less well understood is the impact this can have on the detailing due to the flexibility of the membranes. Thick, bulky membranes may perform well when used in large flat areas with a few complex angles, but when used in situations such as raft foundations, they can be susceptible to certain problems. Firstly, when the membrane is folded around tight angles, the molecular structure of the material can open up on the external side of the angle. This will affect a corresponding change in the partitioning characteristics in that area. Studies suggest this effect can be present at angles as low as 60 degrees for some membrane types. So at the 90-degree angles most commonly associated with foundations, it can have a significant detrimental effect on permeability performance. Secondly, if the membrane is not fully supported at these angles, the weight of any subsequent layers, such as the slab or screed, can elongate the membrane, reducing its thickness and increasing the permeability through the free space in the membrane as the molecular gaps are wider. Taken to an extreme, both of these scenarios could even result in the membrane cracking, splitting or tearing, and in a way which would not necessarily be obvious during a site inspection. Another important aspect of installation is the sealing of joints between adjacent sheets. While welding is undoubtedly a more effective solution, it requires specialist contractors and care and attention during installation. This means that traditional tape joints are often used instead. When tape joints are used, it's critical to ensure that they are done right, as tape joints are a common failure in membrane systems. The correct tape is recommended by the membrane manufacturer and should always be used, and the surface to be jointed must be free from any dirt, contamination or moisture, as this may adversely affect the adhesion. It's also worth remembering that under some circumstances, such as where membrane joints are not compressed by slab or screed, the use of tape joints is not considered prudent by CIRIA. If we look at membrane types, the choice of material used on site must be informed by permeability, chemical resistance, physical properties and the inspected installation procedure. All the possible membrane types in gas protection have pros and cons, and it is important the properties of the material selected adequately address the risk factors present on a given site. When it comes to building on contaminated land, there are no magic bullets or one-size-fits-all solutions. Now let's look at some of the most commonly used geomembrane types. Polypropylene, or PP. PP membranes have good elongation characteristics and are highly flexible. This makes then a good choice where settlement is likely or where complex detailing must be undertaken. PP is, however, relatively permeable to most gases and is expensive. PP membranes also have poor adhesion characteristics, therefore require specialist welded joints rather than tape jointing. PP membranes are traditionally used in water containment applications, due mainly to its suitability for use on larger unreinforced areas. High density polyethylene, HDPEs. HDPE is cheaper and offers good resistance to puncturing, but in comparison to PP is rigid and is therefore both difficult to install on complex details and prone to stress cracking. Any bending of the membrane to angles over 60 degrees is typically not recommended due to its detrimental effect on performance. Because of this mechanical weakness, HDPE is better suited to large uninterrupted floor areas, which is a good fit with roll sizes that they are typically supplied in. Like PP, HDPE membranes should not be tape jointed and require specialist welding contractors and verification. Low density polyethylene, LDPE. LDPE membranes are standard DPM materials which are cheap, easy to handle and readily available, but can be low quality and are generally not suited for gas resistant applications due to their high permeability and limited resistance to damage and UV. LDPE membranes' resistance to VOC transfer is particularly poor, and these membranes can degrade rapidly if directly exposed to chemical contamination. Low-grade LDPE can also have problems with manufacturing tolerances, resulting in a material that, while water-resistant if undamaged, will not deliver consistent and robust performance in gas protection applications. Reinforced virgin LDPEs. Reinforced membranes made from a high-quality virgin LDPE are inherently more consistent, as good control of thickness and material tolerance is critical for achieving a good lamination with reinforcement. This reinforcement also greatly improves the membrane's resistance to tearing and damage while allowing the membrane to retain its flexibility. This results in a good balance of durability, performance, ease of installation and cost. It is, however, important when using these membranes to have a good understanding of the risks present on site to ensure the vapour or gas permeability of the membrane is adequate for the application. Foil-based membranes. Adding a foil core to LDPE or HDPE membranes dramatically increases the gas and vapour resistance of the membrane without a corresponding dramatic increase in cost. This makes them a good option where elevated risks are present and it's not feasible or desirable to use source remediation to lower the concentrations present. There is a common misconception that because the membrane has an aluminium foil in its build-up, that this will offer good all-round protection from contaminants. While that may be true when considering gown gases, there are problems with this assumption, particularly when VOCs are involved. The first problem is reduction in performance over time caused by oxidisation of the foil layer. This can either be caused by damage to the membrane, by exposure to chemical contaminant levels out with its design specification, or at the edges of the membrane where the foil is exposed. Another problem is common on all sites where foil membranes are used, regardless of the presence of VOCs. While the base plastic membranes are able to elongate to some extent, this is not true of the foil layer within them. If settlement occurs, the corresponding stretching of the membrane can rupture the foils, leading to a significant deterioration in the gas barrier performance. It is therefore critical when using foil-based membranes to make sure settlement is minimised and expansion joints are properly detailed to avoid overstressing of the membrane. Foil membranes such as the Proctor Group's Protect GM Super are generally considered a better fit for common ground gas applications such as methane and landfill gases. When dealing with VOC contamination, dedicated membranes such as Protect VOC Flex will offer a more comprehensive solution. Specialist film laminate membranes. These type of membranes are similar to the foil core membranes as above, but replace the foil with a specialised plastic film such as an EVOH. This allows the performance of the membrane to be adapted to meet application-specific barrier requirements. EVOH membranes offer good resistance to a variety of VOC contaminants while still allowing the membrane to retain a good physical performance characteristics such as flexibility and elongation. Liquid applied membranes. Liquid applied membranes are ideal for complicated foundation detailing on uneven surfaces. The downside to these systems is it's not always easy to determine the tolerance of the application, such as the continuity or thickness of coating. Liquid applied systems do, however, make a good companion to sheet membranes where complex details must be sealed. So we've seen throughout today's presentation that the most important factor in dealing with contaminated sites is good design based on good information, whether it's conducting a thorough investigation into historical uses of the site or ensuring the correct membrane for the job is well installed by contractors. A good understanding of the risk factors involved and a well-developed holistic remediation strategy is key to achieving a safe and good value solution. With over 20 years' experience in ground gas protection, the Proctor Group have always taken this approach, supplying both a range of fully tested membranes and comprehensive technical support and design consultation throughout the specification and installation process. We'll now take your questions in the Q&A session.
Hi everyone, I'd like to thank Aubrey for hosting the webinar today. I thought the content was fantastic. My name is Keira Proctor and I'm the Managing Director here at the Proctor Group. I'd like to thank you all for coming and hope that you got some value out of the information that was shared. We're going to take some technical questions now that have come through on the web chat and email. If you don't have time to stay, you will be emailed a replay pack so you can listen to the questions at a later date. And you'll also be sent a survey, so if you can complete that, we really appreciate it because it does help us shape the future content for webinars in the future. So Aubrey, there's a couple of questions come in on the chat and obviously over email just before we started, so I'm just going to ask you them and feel free to answer away. Great. The first one I received was regarding the use of foil membranes in VOC applications and whether that's suitable or not.
Yeah, as we said in the webinar, there's a common misconception that they can be used when dealing with hydrocarbons in a gaseous state. However, depending on sort of the concentration and the type of hydrocarbon, these foil membranes can easily oxidise due to the exposed edges on the cut edges, and the amount of protection they give from hydrocarbons will be dramatically reduced in that case. So you should really look for a proper VOC membrane.
Okay, and a question that's coming from Stuart, which is probably relevant to ask just now. Can you talk us through the most common VOC encountered generally within domestic dwellings?
That's a good question. There's a whole array of different hydrocarbons that can be on a lot of sites, but ones that we particularly come across are benzene and naphthalene, and we would then recommend our VOC membrane in that situation.
Okay, so coming on to his next question, in terms of the most common barrier, that would be the VOC membrane?
Yeah, that would be the VOC Flex, but as I say, we have come across where people have used foil membranes in that situation. Depending on the concentrations, that may be acceptable, but I would certainly push them down the route of the VOC membrane. Okay.
Another question via email, how can I tell a hydrocarbon membrane from a non-hydrocarbon membrane?
Yeah, again, there's a lot of membranes on the market that claim hydrocarbon resistance, but I suppose the only really way to find out how good that membrane is to ensure that it's been tested against the suite of chemicals that are in 748. If you do that, you then know at least you've got a comparable membrane against a whole range of different hydrocarbons.
Okay. Can liquid applied membranes be used in VOC contaminated sites?
Again, there's a lot of liquid applied membranes that have a certain amount of hydrocarbon resistance, but they won't be tested to the same criteria and tests that are in 748. So again, it would be a case of having a look at the particular hydrocarbon and the concentrations of it, and depending on what sort of liquid applied membrane you're using, whether it's acceptable or not.
Okay. One from E. Fisher that's come in the web chat, very friendly, hi there. Do proctors help with detailing the geomembranes?
Yeah, we'd like to think we offer the complete package from specific details right through to if there's venting designs to be done, so the complete package really.
Okay. And last question, which just popped in on email, how can you ensure good installation?
The guidance documents that are out there at the moment state that installers should be certified to MVQ level 2 for installation of a gas membrane. However, with the recommendations in Syria 735, it states that all gas membrane installations should be independently inspected and verified. And assuming that that's done correctly, this should eliminate many poor installations that may have occurred in the past.
Okay. Okay, I don't think we have any more questions, so I'd just like to thank everyone again. This webinar is taking place at our head office up in Scotland, so it's very kind of Aubrey to come up and share his technical expertise with us here. And as I say, I really hope that you've got something out of it in terms of an educational process in the whole question surrounding VOC membranes at the moment. And as I say, if you have any feedback, please complete the survey and keep an eye on your inbox for any other webinars that we may be doing in the coming months. Thank you.
Thank you.